Namaste bachcho. Welcome to the class. Today we're going to tackle a very important topic from our unit on semiconductor electronics, and that is intrinsic semiconductors. Don't worry, I promise I'll make it so simple that you'll remember it for your exams. Bilkul stress-free. Chalo, let's begin.
So एक simple सा सवाल है. Have you ever wondered why the processor inside your phone is made from silicon, which is basically just sand, but a diamond, which is pure carbon, can't be used? I mean, they're from the same group in the periodic table. The secret answer lies in understanding how they conduct electricity, and that's exactly what we're going to explore today.
So here's our game plan for today. We'll start with a very simple analogy to make the main idea clear. Then we'll get into the proper textbook details, for the exam. We'll also look at some common mistakes you should avoid, understand why all this is so important, and finally, we'll wrap up with the key points. Ready? Let's get started.
Okay, before we jump into all the physics and the technical terms, let's use a simple story. I call it the classroom analogy. Trust me, it makes this whole concept feel much easier. So just imagine a classroom at the coldest possible temperature. That's absolute zero, or 0 Kelvin. The classroom is completely full. Every single student, who we'll call an electron, is sitting properly in their seat, which represents a bond. In this situation, nobody can move around, right? This is exactly how a semiconductor behaves at 0 Kelvin. It's a perfect insulator. Why? Because if no electrons are moving, no current can flow. Simple.
Now let's add some heat to the room. The classroom starts to warm up. Suddenly, one student gets a burst of energy, leaves their seat, and starts moving around the classroom. Now what has happened here? We have created a free student. This is our free electron. And we also have an empty seat, which, in physics, we call a hole. This idea of an electron and a hole being created together as a pair, this is the most important concept to understand.
Okay, so that classroom analogy gives us a pretty good mental picture, right? Now it's time to connect that simple idea to the official scientific explanation that you need to write in your exams.
So what is an intrinsic semiconductor officially? Well, the textbook definition is very simple. It is a semiconductor in its purest form. MATLAB, no impurities, nothing mixed in. And its most important property is that the number of free electrons, which we write as n sub e, is always equal to the number of holes, n sub h.
And this diagram from your NCRT book shows exactly what's happening. Look here. In the crystal structure of silicon, the thermal energy, the heat, gives an electron enough of a push to break free from its covalent bond. When it breaks free, it creates one free electron for conduction, and it leaves behind a vacancy, or what we call a hole. See, it's just like our student leaving their seat in the classroom.
Let's break down this process into 4 simple steps. 1. At 0 Kelvin, in a pure silicon crystal, all electrons are locked tightly in their bonds. 2. As the temperature rises to, say, room temperature, the crystal absorbs this heat energy. 3. An electron takes in enough of this energy and, boom, it breaks free from its bond. And 4. This single event creates 2 things, a free, negatively charged electron and a positively charged hole. They are always created together, as a pair.
And this brings us to the golden rule of intrinsic semiconductors. For any pure semiconductor, the number of free electrons, Ne, is always equal to the number of holes, Nh. And we give this value a special name, Ni, which stands for the intrinsic carrier concentration. This formula is absolutely essential. Make sure you remember it.
Let's make this crystal clear with a tiny example. Let's say thermal energy creates 1,000 electron-hole pairs. So tell me, how many free electrons do we have? Exactly, 1,000. And how many holes? That's right, also 1,000. In an intrinsic semiconductor, they are always equal.
All right, now let's focus on something very important. Common mistakes. These are small points, but they can be silent killers. They can make you lose marks in an exam. So let's make sure you don't fall into these traps.
Okay, mistake number 1. Many students think a hole is a real particle, like a proton. No, a hole is simply the vacancy, the empty space, left by an electron. It just behaves like a positive charge. Mistake number 2, thinking that the crystal becomes charged when these pairs are created. Wrong again. The crystal stays electrically neutral. Why? Because for every negative electron that breaks free, a positive hole is created right there. They balance each other out, so the net charge is always 0. Now you might be thinking, sir, this is interesting, but why is it so important to learn this? That's a great question. Understanding intrinsic semiconductors is like learning the ABCD of electronics. It's the foundation for this entire chapter. Let me show you how it all connects.
Think of it this way. You have to know the letters of the alphabet before you can start making words, right? Well, intrinsic semiconductors are the alphabet. Once we understand them in their pure state, we can learn how we modify them by adding impurities, a process called doping, to create much more useful N-type and P-type semiconductors. But without this first step, nothing else will make sense.
And why are those modified semiconductors so important? Because they are the literal building blocks of all modern electronics. The diodes, the transistors, the tiny chips inside your phone and your computer, all of them are built on the fundamental principles that we are discussing right now.
We're almost done for today. Before we wrap up, let's do a very quick revision of all the key points for your exams. Think of this as your final checklist.
So what are the things you absolutely must remember? First, pure semiconductors like silicon and germanium are called intrinsic. Second, the charge carriers are electrons and holes, and they are created by thermal energy, or heat. Third, these carriers are always generated in pairs. Fourth, the number of electrons, Ne, always equals the number of holes, Nh. And finally, the semiconductor crystal as a whole remains electrically neutral.
I'll leave you with one final question to think about. If these pure, intrinsic semiconductors are actually pretty poor conductors, they have so few charge carriers, then how on earth did we make them useful enough to power our entire digital world? The answer to that lies in the process called doping, which we will explore in our next session. Thank you, and I will see you in the next class.